All right, so we're going to start with or continue, I should say, with our introduction to derivatives. We basically just started this topic last time, and so now we're going to take a look at some theoretical results, and then we're going to start learning some of the rules of differentiation, which will give us the ability to solve for a very large number of different problems. So we'll start by looking at the connection between differentiability and continuity. So let's see, we have this graph. Let me put it into the notes so we can see it better. And so you can see we have the interval from c to x. And of course, what we're really trying to accomplish here is solve for the slope of that tangent line right here. And so we're going to start, as we always do, by looking at a secant line. You could start here with a secant line between these 2 points. And then what would happen is, as you gradually shrink the distance between c and x, eventually the slope of the tangent secant line will converge to the slope of the tangent line. Okay. So in other words, as x approaches c, the slope of that secant line is getting closer and closer and closer, and eventually converges to the slope of the tangent line. And it's that slope that we're actually interested in. So the way we formally define that is, if you look at this formula carefully, you'll see that taking the limit, because as x approaches c, and so in the numerator, we have the difference between the two y coordinates, and in the denominator, we have the difference between the two x coordinates. Okay, so in other words, it's just the slope. That what you're seeing there is the slope of the secant line. Okay, so you can imagine as x approaches c, we're getting closer and closer to this point. And then, as we've seen before, that secant line will get closer and closer and closer to the tangent line. And then in the limit, it'll reach the slope of the tangent line, and that is our derivative. So this is written as f prime of c. Okay. Now, of course, if we came from the opposite direction, we'd have to have the same result. Otherwise, the derivative would be we would not be able to find the derivative if this isn't the same coming from both directions. You can see what they've done here. They've got the limit as x approaches c from the left and the right. Let's make that a little bigger. So remember how this works. This means x approaches c from the left. In other words, from the smaller numbers. And over here, x approaches c from the right. They both equal f prime of c. If they don't, then there's a problem. That means the derivative is not defined. F is differentiable on the closed interval AB under two. Well, there are two things that are required. All right, so F is differentiable on a closed interval, meaning that it includes both A and B. Remember how that notation works. We're going to use square brackets to indicate that both A and B are in this interval. When it is differentiable over the open interval, And that means that we're not including either A or B. But in addition to that, we need to specify what happens at the two endpoints. It has the derivative has to exist. That's all we need. It has to exist at both A and B. Okay. If not, well, then it's differentiable in the open interval, but not the closed interval. So um, that's all we need. It doesn't, they don't have to be equal to each other or anything, but we do know that the derivative A and B. So specifically, actually, let me draw this a little better. We need to know that from the right at A and from the left at B. This is what we need to be defined. Now, now look at this thing. You may not have run into this before. Sometimes called the step function, as for obvious reasons. The this set of symbols, these two brackets, are used to indicate this is the greatest integer function. So what does that mean? Well, let's take this as our example. Um, let's say we're looking at 0, then in between, let's say right here at a half. So think of it as the greatest integer that is not greater than that number. Okay. So in other words, in order to get up to 1, from that point on, we need to get it all the way up to 2 to reach the next step, I guess you could call it. Okay, so you notice there's these holes. And so this tells me that the solid circle here means that the function when x equals 0 is 0. And that's going to be the case all across this entire range of values until we get to 1 itself. And then it jumps up to 1. Okay. So now here's the thing though. You can see that the function is not continuous exactly at the integers 1, 2, 3, et cetera, et cetera. So that means precisely at these integers, f of x is not differentiable at x equals 1 or 2 or 3 or any of the others. Okay, because of the discontinuity. The derivative requires continuity. So in other words, that's what we're saying. Now, they're also making the point that it's possible for a function to be continuous and not differential. It doesn't go both ways. If a function is differentiable, then it must be continuous. But if it's continuous, that doesn't guarantee that it's differentiable. So here's a perfect example of that. This is actually very closely related to our old friend, the absolute value function, except that it's x minus 2. And so you can see what it looks like. Now you've seen this before. When it's just y equals the absolute value of x, it reaches the origin right here. Because it's x minus 2, we reach the horizontal axis here at x equals positive 2. So this function is continuous everywhere, but it is not differentiable exactly at 2 because the slopes are different from each other, coming from both directions. Okay, in other words, the derivative of this function below 2 is not the same as this above 2. So at that exact point, there is no derivative. Okay. And so whenever you see in a graph like a sharp break like that, then you know that at that point at least, there is no derivative. There's a derivative everywhere else, but not at that one point. And that's despite the fact that the function is continuous. The problem is that the derivatives are different on either side of the point. So, in other words, under normal conditions, you have a function like this. Let's say that at this point, the function has a derivative of 2. So that means that you can see what's happening as you get closer and closer to that point from the left. The derivative or slope of this tangent line is getting really close to 2, and the same thing is happening from the right. And then they're converging to 2 at that point. So there, the derivative is defined. But when there's a sharp break like this, so that the derivatives are different on either side, and the derivative does not exist at that point. So we have to keep an eye on that. It's possible that there is no derivative, or at least not at certain individual points. So these are the two main reasons why that might happen: discontinuities and sharp breaks in the graph. And they're going to go ahead and prove it by showing you that the limit as x approaches 2 from the left is -1. Okay, in other words, it should be pretty clear that the slope on this side is -1, and this side the slope is +1. So what this suggests is that the limit as x approaches 2 from the left is -1 on the side. Just 1. And so since they're different from each other, the derivative can't exist exactly at x equals 2. And then on the other hand, like I said a second ago, if the function has a derivative at a point that guarantees that it is continuous at that point. In other words, the function can be differentiated at x equals c, then we know for a fact that it's continuous. So, in other words, the logic doesn't flow both ways. This is what they're telling us. If f is continuous at x equals c, that doesn't guarantee that it's differentiable. But if it's differentiable at x equals c, that does guarantee that it's continuous. All right, so let's take a look at this question. Find the slope m of the line tangent to the graph of the function g of x equals 9 minus x squared at the point 4, -7. So g of x, oops, 9 minus x squared. All right, so in other words, they're asking us to find the slope of the tangent line. But we can find that by finding the derivative using the limit definition. Okay, so what does this graph look like? Well, it's an upside down parabola. And let's see, it would look something like this, actually. Let me fix that a little bit. The intercept would be 9, 0. All right, that's probably better. So we have g of x is 9 minus x squared. Now, because it's 9 minus x squared, the 2 points where this graph crosses the axis are so in other words, this point is 0, and this point is -3. So the 4 would be here, and it's going to touch right about here at 4, -7. So they're after the slope of this tangent line. All right, it's not a great drawing, but you get the idea. In other words, where x equals 4, we know that y equals -7. So this is the point on the curve that we're looking for its slope. So we're going to use this formula here to find the derivative at that point because that is the slope of the tangent line. They are the same thing. So therefore, the point C is the 4. We know that f of C is -7. So this is the limit as x approaches 4 of all right, so let's simplify it a little. Okay, so now you can see, actually, let me rewrite it like this. So, well, all right, anyway, you look at it. So we might be able to divide x minus 4 into negative x squared plus 16 and simplify it a little bit. By the way, when you're doing long division like this with polynomials, don't forget about this placeholder here for the x that's missing. So we'll have minus x, subtract, which means this becomes positive, this is negative. And then if we use -4 here, we subtract. So what this means is that this whole expression can be reduced to negative x minus 4. Okay. So the limit of this expression as x goes to 4, if we directly substitute 4 into here, we're going to have a real problem. Okay. So instead, we reduce this. So this is the function 16 minus x squared over x minus 4. So there's going to be a little hole here. So what we can do now is take the limit of this negative x minus 4 so that means the slope at that point is -8. Now, of course, we know that there's a hole here, but the limit still exists because as we get closer from the left and closer from the right, we're still approaching the same point. Okay, so the limit is -8. Limit x goes to 4 from the left. It's -8, and that's the slope of our tangent line. So the final answer is -8. All right. Now, when we learn the rules of derivatives, of course, you won't need to go through this anymore. You'll just use the rules. It's very quick and easy with the rules, but it's again, it's important to understand what's going on behind the scenes and understand where the rules came from. I don't know if I haven't checked if the WebAssign is asking you to do the theoretical results or not, or if it's simply letting you make your own decisions. But anyway, let's take a look at this. Now, they want us to do the same thing. Take the derivative with the limit definition. Yeah. Oh, okay. I just realized I know what they mean at first to do. They want us to take this expression. Yeah, they want us to take this approach. Okay. So let's do that. Because this way delta x is going to 0. We don't have to worry about that. All right, so we just need this part. And the function they've given us is negative 3x squared. Or I'll just copy that. Oh, that's just what I did not need. All right, so the first, what we should probably do first is solve for f of delta x. All right. So remember what's happening here is you're just replacing all the x's with x plus delta x. Now over here, we've got x plus delta x squared. Apply FOIL in this case. F is these two terms. O are these two. I would be these two terms. And then last would be these two terms. So we ultimately end up with x squared plus 2x delta x plus delta x squared. So that's the only part that's going to be messy. So we'll plug that in up here. In the second case, we had 6x plus delta x. Now we can distribute these terms. We might be able to simplify it a little bit. Maybe not. All right, but that's, remember, that's just the f of x plus delta x. We now need to subtract from that delta, f of x rather. So our f of x is negative 3x squared plus 6x minus 8. Okay. So when I subtract, let's see what we get. Usually at this stage, some of these drop out. So we'll drop out these two. A couple more. And there's two more that can go away. So we're left with minus 6x delta x minus 3 delta x squared plus 6 delta x. So that's the numerator of our expression. Now we have to divide by delta x and then take the limit. So this is equal to the numerator of this expression. Now, I did divide by delta x. Now, as it turns out, every one of the terms in the numerator has a delta x in it. So this will reduce very nicely to, let's see, that gives us minus 6x minus 3 delta x 6. Now we can actually take the limit with direct substitution. And because this goes to 0, we'll ultimately end up with minus 6x plus 6. Okay. And we're done. That's it. They just wanted the derivative, but they wanted it done this way. All right, so this is the original expression, and this is our final result. All right. So I think now we're finally ready for our rules. That should be it for the theory. Yes. All right. So that's section 2.1 done. Now let's go on to 2.2. Basic differentiation rules and rates of change. Perfect. All right, great. So there's several rules we're going to be introducing, and that includes trig functions, by the way. So we'll start with the constant rule. Now, keep in mind the derivative is ultimately a slope, which means it's a rate of change. So that means that the derivative of a constant is 0, right? So in other words, the c never changes. So any constant will automatically have a derivative of 0. All right, so don't have to worry about that anymore. And you can see here they're using some different notations. If y equals 7, the derivative, here they're writing it as dy dx, 0. Here the derivative of 0 is just 0. That's here they're writing it as f prime of x. S of t is minus 3. That derivative is, of course, just 0. We write it as s prime of t. And here they've chosen to write this one as dy dx. Since these are constants, they'll just end up giving us a 0. Now, this is a little different. F of x equals x to the n power. So what they're building up to is the power rule. Okay, they want us to see that these are all cases that we might see here. So the power rule tells us what to do when we have the derivative of x raised to the n power. Now, n can be any number, any rational number, I should say. So in other words, it won't be pi or radical 2, but it'll probably be an integer, but it could be a ratio, like 3/2, let's say, or it could be negative. So, and you see the rule is surprisingly simple. The derivative of n to the x to the n is simply nx to the n minus 1 power. How do you like that? So this is one of the more important rules that we'll run across, and it also happens to be one of the simpler ones. That worked out rather well. So just keep in mind the power rule. We're going to see it all the time. So let me just throw a quick example up here for you. All right. So in other words, the new coefficient is the previous exponent, and then the exponent is reduced by 1. That's where this came from. So if you had something like this, Now this time the exponent, as you notice, is negative. We're going to end up with negative x to the minus 1. And we end up with negative x to the minus 2. And if you want, you could write this as, because it means, of course, the same thing. And sometimes you get more complicated cases. Let's say we get something like this. So if I rewrite this as 3 halves minus 2 halves, you'll see that we ultimately end up with or of course, if you prefer, you could write 3 halves radical x because it's the same. All right, then. So I think I have some examples waiting for us. All right, so like x to the third power, I think I just did that one, 3x squared, the cube root of x. So remember, if you rewrite that as 1/3, x to the 1/3, you'll see that you'll end up with 1/3 x to the minus 2/3 power, or equivalently 1/3 to the x to the 2/3 power. Down here we have x, 1/x squared, which is the same thing as x to the minus 2. So the derivative will be negative 2x to the minus 3, or minus 2 over x cubed. Now, if we have a constant in our expression, we can essentially just factor it out. You see what they're showing us here is that if you have the derivative of c times f of x, you just end up with c times f of prime of x. So that means you can start to consolidate some of these rules into more complicated situations. So now, for example, we have y equals 5x cubed. And it might look like it, but we can still use the power rule because factor out that 5 and then apply the power rule directly to x cubed. Very clever. Okay, how about 2 over x? So again, you can think of it as 2 dy dx of x to the minus 1. All right. And then here we have 4/5 t squared, to the, sorry, 4/5 t squared, yeah. Oops. So, yeah, this time they're using a prime, but we can also write it as like this. So the derivative of t squared by itself, based on the power rule, is 2t to the first power. So we'll ultimately end up with 8/5 t. Oh, and there's more. Okay. Let's try another one. Y equals 2 radical x, or in other words, 2x to the 1/2. Okay, so I apply the power rule to x to the 1/2. It becomes 1/2 x to the minus 1/2 because I'm subtracting 1 from a half over here, eating that up a bit. Okay, so this reduces to x to the minus 1/2, which is actually the same thing as 1 over radical x. Okay, now, oh, this one is interesting. We have to keep an eye on the ones that look like this. We're looking at 1 over 2. So here's what we have to recognize. This is the same thing as x to the 2/3 power, because what you're basically doing is you're taking x squared and then you're raising it to the 1/3 power, and you end up with x to the 2/3 power. But we have it in the denominator. Not that really, I mean, so I think what we should probably do here is, because it's in the denominator, what we actually have here is minus x to the 2/3 over 2. All right. So, or you can think of it as 1/2. Oh, wait, what did I do? No, not minus x. X to the minus 2/3, sorry. So it's 1/2 x minus 2/3. Well, now we can go ahead and use the same approach we've been taking all this time, meaning that we do have a constant in there, which we can factor out, and then we can apply the power rule to x to the minus 2/3 power. All right, so that's going to go minus 2/3 x. And by the way, when you subtract 1 from minus 2/3, you end up with minus 5/3, because all right, but you got a half and negative 2/3, so you ultimately end up with negative 1/3 x to the minus 5/3. That's the final result. They've chosen to write it like this: minus 1 over 3. Um, because it means the same thing. All right. Or, oh, actually, I see what they did. They just wrote it as 5/3, but it's the same thing as that. And then this last one is just simply minus 3x over 2. All right. So once again, we do have a constant on the front. Remember, the derivative of x is just 1. Okay. Why is that, by the way? That's a special case. Um, if y equals x, remember, there's an implicit 1 for the exponent. So therefore, dy dx using the power rule will be 1 x to the 1 minus 1 power, which is 1. Okay, so those are the two special cases you should memorize. The derivative of a constant is 0. The derivative of x by itself is 1. Okay, that'll come in very, very handy. Right now, and then they're just bringing them together. The constant multiple rule and the power rule can be combined into a single rule. So you can just take an expression like this, and just when you're done, you'll end up with c and x to the n minus 1. Okay, so that's all there is to it. Now, here's something you're probably not going to be too surprised by. The derivative of a sum is equal to the sum of the individual derivatives, just like with limits, if you remember. And the derivative of the difference of two functions is equal to the difference, the derivative of the distance equals the difference of the derivatives. Okay. So that's a very straightforward idea. And so they got some examples here. So basically, when you have a polynomial like this, x cubed minus 4x sine. So f prime of x, or dy dx. Now here, what they're basically telling you is to think of this as three separate derivatives all being combined into a single derivative. Okay, now you don't have to go through the trouble of doing each one separately once you understand the rules. So, but be aware that you might need to use a different set of rules for each term. But ultimately, no matter how you go about this, at the end, you're just combining them. So you're going to have here, the power rule gives us 3x squared. Whoops. Sorry, wait a minute, hold on. So in other words, this one, based on the power rule, is 3x squared. And of course, this one is a constant. So you ultimately end up with 3x squared minus 4. Oh, whoops, what did I do? All right, then. Let's see, what else do they have for us? Negative x to the fourth over 2 plus 3x cubed minus 2x. All right, so again, we're basically breaking this up into three separate terms. We're taking each derivative separately and then combining them. This one is equivalent to, so you can rewrite this first one as the derivative of x to the fourth is 4x to the third. So, um, so when you multiply negative 1/2 by 4, you'll end up, of course, with negative 2. And this is your final result. Okay. So yes, you can see here, I've broken it up into steps. So you can see that, but these are all applications of the power rule. The last one, too, because that's where that's coming from. All right, now what else? Look at this one. Oh, they've helpfully advised us to rewrite it slightly. X squared minus x plus 1 over x. So, sometimes this helps, you might be able to simplify it like this. It does make things a little simpler. I'll tell you why, because we haven't yet seen how to take the derivative of a quotient, which would be necessary if we're not able to simplify this. So you're going to end up with 3x minus 1 plus 1 over x, which is the same thing as 3x minus 1 plus x to the minus 1 power. So now, of course, we'll apply the power rule to all three cases. Remember, the derivative of x is just 1. This is a constant. It's just going to be 0. And that's going to be our final answer. Or we could write it like that. Oh, I see what they did. They decided to bring it back together as a single ratio, which is fine. You could do that too. Um, if you don't want it written like this, you could write this as, of course, it means the same thing. Now we're looking at, of course, the trig functions, and they all have derivatives of their own. In some cases, the derivative is very simple. In some cases, it's very messy. The derivative of the sine of x is simply the cosine of x. But the derivative of the cosine of x is the negative of the sine of x. These are two you should probably try to memorize. That'll really come in handy when you're using trig derivatives. At least remember those two. Now, if you can't, it's okay. You can always go to the internet and find a chart with all these spelled out for you, but there's certain ones that would probably help you to remember. Therefore, well, let's look at the consequences of these. Um, so we'll start with y equals 2 sine x. So you can think of it like this. I just factored out the 2, and now I can just apply this rule directly, and I end up with 2 cosine x. So that was pretty straightforward. What about this one? Ooh, well, it's just 1/2 sine x. It's going to be exactly the same thing, except the constant is different. So it'll just end up with 1/2 cosine x. All right. Y equals x plus cosine x. And you can see the rules apply here, just like we did before. We're basically calculating individual derivatives and adding them up. So in the first case, we're taking a power rule. This is x to the first power. So this is just 1, and this is now, actually, we should put it as minus, because just as a minute ago, I showed you that the derivative of the cosine is negative the sine of x. Well, all right then. And now we got one more. By the way, I just noticed, I forgot, I wasn't looking carefully enough. On the right-hand side, they suddenly switched the notation to y prime. I guess they want to get you comfortable with all the different ways of expressing the derivatives. Here they were using the f prime, I think earlier they were using dy. Yep, there it is, dy dx. And all of a sudden they switched to y prime. Just be aware, they all mean the same thing. So just as a quick refresher, yeah, okay. It's all the same thing. What else? Cosine x pi over 3 sine x. Well, the pi over 3 is just a constant, so you're going to wind up with, oh, negative sine x minus pi over 3 cosine x. Because it's the same thing as minus pi over 3 and we're all set. All right. Well, so far it seems very straightforward. Now, keep in mind too, these derivatives represent a rate of change of some kind because they're ultimately slopes of tangent lines. So what they're trying to do is give you some insight into why derivatives are so important, because in the real world, a lot of applications do revolve around rates of change of one variable as a result of the change in another variable. Like if a farmer wants to know, if I change the amount of fertilizer that I use, what is the change in my crop output, that kind of thing. So now this is getting into physics here. And what they want you to know is if S is the position of an object relative to the origin, and the change over that is this, then the rate, which is distance over time, tells us that the average velocity is the change in the distance over the change in time, or delta S over delta T. So in other words, if you're given a function, like here, the distance function, which is what that is, distance from the origin means how far up in the air it's gone, negative 16t squared plus 100. So the average velocity, let's see. So on the previous slide, they told us that the average velocity is, but in the limit, this could be written as ds dt. In other words, as the change in t becomes infinitesimally small, what happens to the height of this object? And that's what we're aiming for here. We're looking for the derivative of this function with respect to t. Minus 32t. And oh, I see what they've done. They want us to actually change the actual change. They want us to do it as actually delta S over delta T. So in other words, first of all, what is this thing? It's and they want us to look over the interval 1 to 2. So they basically are asking you to look at the change in S over the change in T. Now the change in T is just 1. Okay. Um, And we can think this is T1 and T2. So S of 2 means $36, S of 1, 4. So when we plug in these numbers, we're going to get so in other words, it's minus 48 feet per second. If we do the same thing for 1.5, you can see that it's going to be negative 40. And then from 1 to 1.1, negative 33.6. And yes, these are all negative because the object has fallen to the ground. So in the limit, see, this is what they're really building up to. And they'll run it, they'll throw this at us again in the future. Velocity is the limit, as delta t goes to 0. And you could, if you think of this as t and t plus delta t, that's what this is all about. And then this distance is delta t. So this is the exact same formula we had before, except that they're using s's and t's instead of f of x and c. So the velocity is the rate of change of the position with respect to time. All right, so I'm sure they'll ask us a few of these in the MindTap or WebAssign problems. Then they also make note here the word speed refers to the absolute value of the velocity because this velocity can be negative. Meaning it depends on which direction the object is moving. So they're giving us this example. Here's a free-falling object under the influence of gravity, where g is a constant, which is approximately 32 feet per second. Yeah, I'm sure you did all this in high school physics. And so we've got a diver diving off the diving board at time t equals 0, and it is 32 feet above the water. So if you take this function using g is 32, the diver, according to this, the initial velocity is 16. And the board is 32 feet in the air. Okay. So that means this is the initial position. And this is the initial velocity. This is sometimes called the gravitational constant. So what do they want to know then? So if you plug in all these numbers, no, wait, sorry, they gave us the initial velocity at 16. Oh, I have room over here. And then S0, the initial position is 32. Um, no, I left out the T. Okay, now we're good. So in other words, they're basically telling us what belongs in this equation. Let's just summarize that here. Oh, and of course these become negative 16, so we don't want to just leave it like that. All right, with all that being said, when does the diver hit the water? Now that means that S is zero. S, remember, is your position relative to the Earth. So in other words, we're solving for S equals zero. Now, while this looks like a mess, you can actually simplify it by dividing out both sides by, let's do negative 16. And I think you'll find it easier to factor it out. Now, here's an interesting twist. We can see there's two solutions. In fact, I'll tell you what, let's put this in Simple Lab and see what it looks like. Okay, so again, it is negative 16t squared plus 16t plus 32. Yeah, up and down. All right. Now, of course, if you look at carefully, you'll see yes, there are two solutions, but because this is a physical application, the t can't be negative. And they're pointing that out here too as well. So in other words, it has to be two. Okay. In other words, you're going to be hitting the water at 2 seconds, not negative 1 seconds, two. All right, fine. The velocity is the first derivative, and applying our rules here, s prime of t, the velocity will be negative 32t plus 16. So therefore, evaluating it at time t equals 2, how fast are we going when we hit the water? It's 48 feet per second, and that's negative because we're going down. All right, well, that's that. That's our physics for today. And now we've got some practice problems. So first we have f of x equals minus 5x cubed minus 2 sine x. So we're going to use the power rule for the first term and the one of the trig rules for the second one. So remember, so I held the negative 5 outside, then I applied the power rule to x cubed. And this is the final result. Okay. What does that mean? Which one is that? Minus 15x squared minus 2. That would be D. All right. Now we've got a physics problem. Okay, so we have ST negative 16t squared plus V0t Remember, the V0 is your initial velocity, the S0 is your initial position. So S is 300 and velocity is minus 12. We're going down, dropping the ball off the roof. What's the velocity? Now, after 4 seconds. So remember, velocity negative 32 minus 12. And then they want to know after 4 seconds. So you're solving for V of 4. Oh, I shouldn't have like this. Just it's 32. Oh no, that's right. That's right. Let me make it a little neater. And it's like feet per second or whatever. So that would give us the letter C. Okay, great. Okay, now that was 2.2. Now, what there's still building up here is there's more rules coming our way. And of course, we're going to see more complicated rules, as you can probably imagine. For example, how about the product and quotient rules? In other words, what if I have the derivative of a product of two functions or a quotient? Well, unfortunately, it's not as simple as it sounds. It's not the case that the derivative of a product is the product of the derivatives. Same thing is true with the quotients. The rules a bit messier. Higher order derivatives, you actually can take the derivative of a function more than once. Okay, so this is where we're headed. So the next section we'll be looking at these more complicated rules, and we'll be introducing the idea of what are called higher order derivatives, the second derivative, the third derivative, et cetera, et cetera. Okay, so something to look forward to, and I'll see you next time.